Good afternoon, sir. My name is Priyanka Singh and my project topic is simulation and performance analysis of a neo-FDM-based communication system. Before I start to talk about my project, I would like to run the simulation so that it comes in time. Otherwise, it might take very long because it has lots of data. Okay, so the objective of this project is to implement a neo-FDM system and to simulate the EEL performance of a neo-FDM system. By available literature, as I came to understand that modern communication system requires better data rate and higher bandwidth consumption. Therefore, a spectrally efficient system is required, for which MemoFDM is a perfect solution, and it also has a great ability to overcome deep fading. For a MIMO system, first I'll talk about a MIMO system. A MIMO system means there will be multiple receive and multiple transmit antennas. For example, I have a 2x2 MIMO system, 2x2 MIMO system, 2 transmit and 2 receive antennas. As we can see that from each of the transmitter antenna to each of the receiver antenna, there exists a different channel. So there will be 4 channels. So if I have a new system where I have entire number of antennas and NRX number of receive antennas, I will have entire multiplied by NRX number of channel, and hence this many impulse responses. So H is the matrix of the impulse responses, and if X is my transmitted data symbol and Y is my received data symbol, then X and Y are related like this, where N1, N2, N3 are noise at receive antenna 1, receive antenna 2, and receive antenna 3. So here in my project I have used Alamuti spacetime block coding. Alamuti spacetime block coding determines how the data in a MIMO system is transmitted across space and time. In Alamuti, what we do is with the first time slot, the first antenna transmits x1, the first antenna transmits x1 and the second antenna transmits minus x2 conjugate, and in the second time slot the first antenna transmits x2 and the second antenna transmits x1 conjugate. So we see that although we have two receive antennas and 2 transmitter antennas, we are still taking 2 time symbols to transmit 2 symbols. Therefore our data rate remains constant, it doesn't get double. In FDM technology, we know that if 2 sinusoids have a frequency difference of 1 by t, where t is the symbol duration, or multiple of 1 by t, then they are orthogonal to each other. In FDM technology, we modulate our data symbols with such orthogonal sinusoids, and then add them up and transmit them to the channel. This is a FDM signal where xk is multiplied with a sinusoid that has frequency of k by t. This is important to maintain orthogonality between the transmitted symbols. Then they are added up together and transmitted onto the channel. As we can identify, this equation is similar to the equation of IDFT. Therefore, FDM modulation is equivalent to performing IDFT or IIFT, and demodulation is therefore equivalent to performing FFT or DFT. If we are talking about FDM, it's important to talk about cyclic prefix. Cyclic prefix is the data that is appended to the data so as to create an interval between 2 data, so that there will be no interference between the two. This is a Wavian chain structure. As we can see, first data are modulated using BPSK, QPSK or any other modulation. Then IIFFT, that is OFDM modulation, is performed. After that, interval is inserted by means of cyclic prefix. After that, it's passed to low filter. Then up conversion is done. It passes through channel, reach the receiver. Down conversion is done. Then it's converted into digital form. After that, cyclic prefix is removed. After that, FDM demodulation is done by performing FFT. After that, the BPSK, QPSK or whatever modulation was done earlier, the demodulation for the same modulation is used, and the data estimate is obtained. So, a FDM system has the is the advantage of eliminating interference, and it is also very good for hardware implementation because the equalization happens in FFT in frequency domain, so the calculation complexity is much less. Therefore the hardware implementation becomes easier, and also the spectrum, also the use of spectrum becomes better. Mimo system is also spectrally very efficient, but the problem is that it cannot overcome deep fading, which OFDM is good at. Therefore, a solution is to combine both of them. This slide shows a Mimo FDM model. In this Mimo FDM model, as we can see, first random data are input. After that, constellation demolition like UPSK or QAM is done. After that, space-time block coding, that is Alamotti space-time block coding is done. After that, the OFDM modulation is done, and then they are transmitted through the multiple antenna. Then they arrive at the receiver. After that, the OFDM demodulation is done by performing FFT. After that, space-time block decoding is done with help of equalization matrix. After that, the constellation demodulation, that is QPSK, QAM, or whatever modulation was applied, the demodulation is done, and the data estimate is obtained. So this entire OFDM system is divided in three parts in my project: transmitter, receiver, and cyclic prefix. As I already talked, transmitter performs BPSK, STBC, and OFDM. Receiver does the reverse process, and the channel here is chosen to be Rayleigh channel. And number of type is chosen to be 10 because the frequency is 20 megahertz. As I stick to the IEEE 802.11a specification, so the delay spread is 10 by 20 megahertz, 0.5 microsecond, which is less than the 0.8 cyclic prefix in duration of 0.8 microsecond. So that the system is able to avoid the interference. This formula is the formula bit error rate of a OFDM system in an n-type Rayleigh channel. So these are the OFDM parameters which can be found at the IEEE 802.11a specification. Also, I won't go through them because it will take a lot of time and they are self-explanatory. The algorithm is to first generate 0 and 1 with equal probability. After that, BPSK is done, and then they are grouped together of two symbols as they have two receivers. After that, Alamotti space-time block coding is done, and then the OFDM has to be done. So before that, the space-time block coding, the space-time block code data that grouped into OFDM symbols, and then carrier frequencies of -26 to -1 +1 to +1 here assigned to the first 52 bits of OFDM. Then these are transmitted to the channel, and therefore converge with the channel frequency response, and AWGN is also added. After that, they come to the receiver, and at the receiver first the cyclic prefix is removed, and then FFT is performed, that is OFDM demodulation is done, and then equalization is done, that is the space-time block coded decoding. After that, it is fed to a decision device where it performs hard decision decoding on the data, and the output is the data estimate. Then the data estimate is compared with the original data, and the different number of data that don't match with the original data gives me the BER when divided by the total number of data. This step 1 to 13 is repeated for multiple SNR values as I intend to get a BER versus SNR curve. So in the simulation, we have seen that I'll just show you the simulation as it has come up. The blue line corresponds to a Mimo FDM system, and the pink line corresponds to the theoretical BER for a Mimo system, only Mimo system, and this is for only OFDM system. As we can see that the BER performance of a Mimo FDM system is much better than that of OFDM and Mimo. Here I have shown a 2x2 and 2x3 Mimo system. We can see that as the number of receiver antenna increases, the bit error performance becomes better. The same pattern follows when the number of received antenna is increased to 4, the bit error further goes up. I conclude that MIMO FDM has a much better error performance than MIMO and OFDM individual system, and as the number of visible antenna increases, the bit error rate performance improves. A future work can be done by varying the number of subcarriers in OFDM system and watching the bit error performance for that. According to theory, as the number of carrier increases, the interference increases. Therefore, bit error rate performance should degrade with increasing number of carrier frequency. Thank you.